So we will now start another topic of our course, that is biomaterials. Okay, in today's class, we will just merely start it, and then we will finish up today's class and we'll continue tomorrow. Okay. So what are biomaterials? So very simple definition is it is a non-viable material, all right, and it is used in medical devices intended to interact with biological systems. So those materials which are non-viable means they are not living. They are used for making medical devices and they are going to interact with biological systems. So when a material fulfills all these three criteria, it is called a biomaterial. Now, if you remove the word medical device, so then the application means a much more class of like much more wide variety of materials will come under the umbrella of biomaterials. So what I'm trying to say is material need not be used only for making medical devices. It can be used for other purposes as well, where that material is being coming in contact with biological systems. So one small example is your with artificial tissue construct actually. So that is not a device. It means you are not like programming it to do some particular function, but it's a biological tissue, biological thing which is going to come in contact with your body. By medical devices, I mean the pacemakers, okay, or the prosthetics, same. So those are basically come under the broad umbrella of device fabrication. Also, there are sensors or bands, wearable sensors, etc. These are all devices. So, and another word that is non-viable. If you remove this word from the definition, then also another very large class of materials can be called biomaterials. For example, the bioink, okay, where you have added living cells in it. So the bioink now can be called a biomaterial. Okay, and these bioink is used for artificial tissue, and that is use. That is actually the work. That is the work of tissue engineers to make artificial tissue. So, which is why the biomaterials are, is very important for us to study when you are studying the course tissue engineering, because without materials you are not be able to create the ECM artificially. And you know the cells need an ECM not only for mechanical support but also like cell-cell interaction. Okay, then often the ECM gives us some signals, survival signals, etc., to the cells so that it can do its function. Okay, so you need an artificial ECM, and often the biomaterials are used for making an artificial ECM. So biomaterials science is basically now a field, which is a very big field, and many researchers only work on developing new types of novel types of biomaterials. So it's a field where the physical and biological studies of materials are being done and their interaction with biological environment. Okay? How these materials interact with biological environment and what is their physical and chemical properties, etc. that is being studied in this area. Now, another very important term that you will often find in literature, that is biocompatibility. So we usually use this term biocompatibility in our discussions, but it has a particular meaning. So it means if a material that is chosen is giving the appropriate host response. So your biomaterial is going to interact with the biological system. So once it interacts, it's going to uh, give some response. The host will respond to it in some way. But if it is appropriate, okay, then you will say that the material is biocompatible. Okay, appropriate for what? For that particular application. So one example, few examples you can is given here. Appropriate host response for, say, medical device sector can be resistance to blood clotting. Okay? Your device should not trigger the clotting of blood, like the uh, membranes that is used for hemodialysis, etc., where the body blood is coming and then going. So their clotting should not happen, right? Then resistance to bacterial colonization. Then, if we are making artificial tissue, then we should promote only normal, uncomplicated healing. Complications should not come. So these are the appropriate post response that we look into a biomaterial that is being used for a particular application. So, applications being hemodialysis membrane, just I talked about that this hemodialysis membrane it should be such that it should resist blood clotting. Then the catheters that is used, urinary catheters in patients who cannot go to washroom by themselves, so they have to urinate in a pan. So catheters are attached to their bladder. So these within this catheters, the material that is being used to make these catheters, it should resist the colonization of the bacteria. Okay, so that the patient does not become septic, as well as when you are using prosthetics like the hip prosthetics, the knee prosthetics, mm, when after like surgically implanting into the body, they should promote normal healing, not complicated healing. So these are the applications for which various materials are being used. Okay, and from this material, we expect some appropriate host response. So when this host response is observed, we say that the material is biocompatible. All right. So now the definition will become much more clear. Biocompatibility means the ability of a material to perform with an appropriate host response in a specific application. All right. Now let's see what are properties of a biomaterial one should study, all right, or in order to understand that material much more deeper. Okay, so it becomes very important when you are trying to understand which material to use as your say artificial ECM for making a tissue. Okay, when you want to answer this question, then you have to look into what properties does it have. All right. So whether this property is going to match with your application, or whether the properties of this material is making it going to make it biocompatible or not. So this for this question, we have to look into the biomaterial properties. So biomaterials are characterized by the interaction with biological molecules, cells, and tissues. Right? Is how they interact with the biological systems. So as in case with all materials, any kind of material, it is similar, same for biomaterial as well. We have to uh, see that there is a surface, okay, surface of the material, and there is bulk of the material. Bulk means the core of the material, and surface is what you see on the faces and the edges, right? That is the surface. The surface characteristics is always different from the bulk characteristics. So people study both the surface characteristics as well as the bulk characteristics when they are trying to understand a particular biomaterial. And biological response. So both these surface and bulk characteristics, they contribute to some biological response. All right. Say it is the cells usually see the surface. All right. So how is the surface? How the surface being modified, etc., will affect your cell behavior. And the bulk, that is the core of the material, often contributes to the strength of the material. And uh, strength of the material will dictate its use for a particular application. Means if you want to make a prosthetic, you will choose the material which is very high, which is of very high strength. Whereas if you want to implant something on your heart, then the strength of that material should match with your heart muscles. So this kind of characteristics people have to understand okay, before choosing it for a particular application. So first we will look into the bulk properties. Okay, so how the bulk properties comes, okay, means what contributes uh, or what is going on in the bulk of the material. So these materials are solids, right? And solids are different from other state of matter like liquids and gases because the atoms in solids they are held together by strong interatomic forces. And mainly there are three types of interatomic bonds, primary bonds known to us. One being ionic bonds, covalent bonds, and metallic bonds. So briefly, what is ionic bond? So there within the material there will be some cations and there will be some anions. There will be opposite charge. So they will attract each other by electrostatic effect or a Coulombic effect. Okay. And in ionic solids, what happens is the positively charged cation is surrounded by as many anions as possible. Okay, so that the cations don't face repulsion in between. Okay, and in when this kind of arrangement takes place, it is a very highly ordered arrangement because of which the ionic solids have a crystal structure. And these solids do not have any free, loosely bound electrons roaming around, because of which they are very poor electrical conductivity. They have poor electrical conductivity, as well as loose electrons will contribute to higher chemical reactivity. But since there is no loose electrons, the chemical reactivity is also low. Some examples of ionic solids being the salts like sodium chloride, magnesium oxide, calcium chloride, etc. These are the ionic solids where ionic bonding is there between cations and anions. Then there are covalent bonds also possible. These bonds is formed because the valence electrons are being shared, and here also crystal structures can be formed by the atoms, like diamond and then graphite that is made up of pure carbon. Both of them have a different crystal structures, right? So the difference in crystal structures gives rise to difference in their properties. And since there is no free electrons within the structure, within the crystal structure, because of that, they are poor electrical conductors. Now, there is another class of primary bonds that is found in solid is called the metallic bonding. So, metallic bonding, you can obviously understand they will be found in metals. Here, what happens? The electron donor usually uh, the atom, okay, which donates electron. So that is positively charged. So that is surrounded by valence electrons. Means these electrons where it will go. It is going somewhere, right? So they are not accepted by other electron. Rather, they are like roaming around the donor atom, like, and forms a cloud or a gas. Okay, so when this kind of structure is there for an atom, then a large many atoms which are positively charged, all of them are surrounded by electron clouds. They are come together and they are bonded only because of the presence of these electron clouds. And there is some what is the charge neutralization because of the negatively charged electrons and the positively charged core atom. So this kind of bonding is called the metallic bonding. This is the free electron model that explains how the metallic bonding takes place. So the non-localized bonds within the metal crystals, it because of this kind of a structure, it permits plastic deformations. Means plastic deformations means uh, the material extends so much, right? The material extends so much that uh, it reaches a point when you give some tensile force on the material, okay, it is extending, okay, it is in the elastic regime. Means when you remove the force, it will come back to the original length. But plastic deformation regime is that regime when you are giving so much force to the material that a point comes when, after removal of the forces, the length of the material does not go back to its original. The uh, force has caused a permanent change in the length of the material. That that is called plastic deformation. So this kind of structure, electron model, free electron model due to metallic bonding, this kind of thing, because of this, metals often have the capability to undergo plastic deformation. And because of presence of free electrons and moving around, as these metallic bonds contribute to solids which are having high chemical reactivity and high electrical and thermal reactivity. Means they are a very good uh, conductors of electrical current and heat as well. Okay, so these three types of primary bonds, strong primary bonds, are there, that is found in solids, okay, in general. But there are also some weak bonds, and these weak bonds are often important when we talk about a class of material called polymers. Okay, polymers are nothing but monomer that is covalently linked with large number of monomers and form a polymer. A small unit is called a monomer, and when they are connected, and it forms a polymer. So in polymers, the structure of the polymer, in the structure of the polymer, there are often various kind of weak bonds that are available. So two of these are the van der Waals bonding, and there is the hydrogen bonding. Okay, so I have like in my simple discussion, I have like slightly hinted on the classes of the material that is available to us. So this is the complete basically list. So mainly there are three classes of materials that people use uh, in general. Okay, and all three, when you see the examples, you will find few metals, use few types of ceramics, few types of polymers. They are also biomaterials, means they are used for making devices or for making tissue constructs that comes in contact with biological systems. So what are the three classes of materials? Broad classes. One is the metals, second is the ceramics, all right. Third is the polymers. Now, based on the origin of the polymers, like how they are made, you can again classify them as either natural polymers and synthetic polymers. Okay. So briefly about the three classes of the material. So metals, they are having in these metals, the atoms are linked by metallic bonding, all right. And you can make you can use pure metals, or you can mix various kind of metals, liquid in liquid molten state, and create alloys, all right. Now there is another class called ceramics. Now the ceramics, here the atoms are linked together by ionic and covalent bond, like they are present in a combination, various combination, and they are basically inorganic in nature, all right. Means the inorganic elements, they are used, they are present in the ceramics. Under ceramics, there is one more class of material that is called the glasses. Okay. So, what are glasses or inorganic glasses are also called bioglasses. So, these are ceramics only, but when they are first they are melted, they form a stretchy, gooey kind of a structure. But when this structure is cooled, okay, when this state is cooled, it does not go back to a crystal state. If you recall, the ionic bonds and the covalent bonds contribute to a crystal structure. But no, initially the crystal structure is there for the inorganic gases. When you heat it and convert it into a molten state, and again then you cool it, the crystal structure is not, original crystal structure is not maintained. It happens because there is a rearrangement that takes place in the placement of the atom that makes the cool down structures amorphous. Okay? So this is the characteristic of inorganic gases. Now, the third class of material is called polymers. Now, the polymers, as I told you, are nothing but various monomers or unit, small unit that is being joined together in a joined together through a covalent bond and form a chain-like structure. So, in polymers, the main or the primary bond that is there is the covalent bond. So due to covalent bonds, these polymers are formed. Okay. So based on the difference on what kind of atomic bonds are there, the characteristics of the material has changed, and because of which we are able to classify it into different types. Okay. Now, in among when you're studying the bulk properties, you have to one bulk property you have to consider is the mechanical property. So under mechanical property, when I was talking about the strength, right? So here, when people study mechanical property, they basically study the strength of this material, how hard it is, how soft it is. Okay, so these studies are being done. So characterization of mechanical properties of materials is important for matching the for matching the properties of the biomaterial to the in vivo environment. Okay? So our body, or the tissues in our body, they have some strength. Okay, they have some hardness associated with them. So what people try to do is they try to use that kind of that biomaterial, or they try to use an appropriate type of biomaterial with whose strength is similar to that of the local tissue. So you for making a prosthetic for your bone, you would choose a material which is having strength or similar to your bone, like in that is present in our body. So which is why people use metals to make broad prosthetics. They don't use polymers. Polymers generally have very low strength in comparison to metals. Okay, so you have to match the strength of the local tissue where your artificial tissue or your prosthetic or whatever device that you're making is going to be implanted. Okay, so if it doesn't happen, if you don't, if you're not able to do it, then there will be failure of your device or the artificial tissue won't graft on your location properly. Okay, and this kind of failure can be catastrophic. So that is why studying the mechanical properties of the material becomes very important. As a starting point, it is important to recognize that tissues can be described using theories of elasticity and viscoelasticity. Okay, so what are these theories? We'll briefly touch upon that now. So the theory of elasticity basically describes the elastic behavior of the material. Okay, and the elastic behavior of the material is described by the linear stress-strain relationship, that is the Hooke's law. So Hooke's law. Mm, okay, so in Hooke's law, so this is the stress, this is the strain. Okay, sigma stands for stress, and epsilon stands for strain. So there is a linear region, okay, where stress is proportional to strain. So this region is given by the law. Okay, and this is the elastic region. Means whatever stress that you, so whatever strain that you apply, okay, means you are increasing the length, say by giving some tensile force on your material, and if that strain is within this stress limit, when you remove the forces, the length will go back to its original one. So that is the elasticity. That is what is called elasticity. And the elasticity can only be seen in this linear region. Okay, the stress is proportional to strain. Okay, so whatever strain that you're applying to the material, equal amount of stress is experienced inside the material. Okay, now stress is basically normalized load and it is given by force per unit area. Strain is nothing but normalized deformation and is given by change in length by original length. So we normalize it because we want to compare uh, among various geometries. Okay, the geometry of your material, if it changes, then the amount of load that is that is required, it becomes different. So we want to standardize that for all different kinds of geometries, whatever value of stress that we will get for the same material should be same. Okay, that is why we use normalized form. And this normalized form is called stress, and this is called strain. So normalization basically helps you to uh, make your data uniform, make your data comparable throughout. Okay. Now, in the linear regime of stress strain curve, a material behaves like a spring. Okay, means whatever force that you apply on a spring, and when you release that force, the spring goes back to its original shape. It is the elastic nature. It is there in the linear regime, that is the Hooke's law regime. But when you go like far from the linear regime, then the deformation happens. That is called the plastic deformation. So, sorry. So here in this curve, this is the linear regime, all right? And then you can see there is a uh, like line that is not linear anymore. It is it is like a small arc kind of a thing. And in this region, the stress is not proportional to strain. Means if you remove the external uh, load, the material won't come back to its original shape. Some permanent deformation has incorporated into that material and means the atoms inside the material, they have permanently changed their positions, okay, and occupied new position in the material, all right. So because of which that structure has become now permanent. Okay, now from the Hooke's law, I said stress is proportional to strain. So one proportionality constant will come. That constant is called Young's modulus, and it is given by E. Okay. So we for a particular type of material, we measure the Young's modulus, and Young's modulus can be measured from the slope of this linear region. That is the value of Young's modulus. And Young's modulus is basically intrinsic to a material type. So when you are comparing various type of materials, say a metal or a polymer, etc., we compare the value of the Young's modulus, and from that value, we say uh, like if this material is very hard or if this material is very soft, etc. Okay. Now, this stress can be of tensile nature, means your forces are towards the outwards. Okay, you're pulling your sample, that is through tensile forces are there, and compression, that is you're compressing your sample from the both sides. So you can either do tensile forces, you can either apply tensile forces, then you will get tensile stress and tensile strain, or you can give compressive forces, then you will get compressive stress and compressive strain. Okay. Now, another way of applying force is by shear. Okay. So, what is shear, or how does shear force look like? So, let me show you an image. Okay. So this is another book that I'm showing you guys. This is called Biomaterials Science. and I have used this book to cover few of the topics in the biomaterials section. So I will like give you the reference details of this book so that you can download it and keep it with you, and in case you need it, you can refer to it. So this is how the tensile strain and the tensile stress look like. So this is a sample, and you are giving force from the both ends. Here force is applied, here also force is applied, and you are pulling the sample. So if this is the uh, like if L naught is the original length, due to tensile force, some additional length has been added, that is delta L. So then the tensile stress can be expressed by F by A. A is the perpendicular area perpendicular to this force. This is A. Whereas strain can be expressed as change in length, how much additional length has been added due to force, that is delta L, squared by L. Okay. So what is shear? So shear is when you give some tangential force on the material. So the bold lines or straight lines shows the original shape. Okay. And when you apply a tangential force on, say, this face, this shaded face of this block, and the force is applied tangentially in this direction. See, you can see the arrow, because of which the shape of the material, it has slanted, right? It has slanted. So if this is delta L, so sorry, if this is the original length of this face, this much additional length is being added due to this tangential force. So from that you can then calculate what will be the shear stress. So shear stress will be F, which is the tangential force, divided by the area that is parallel. Note here we are taking the uh, area that is parallel to the tangential force, okay, to calculate the shear stress. Whereas for the shear strain, we are using a change in length that has happened due to the shear force divided by the perpendicular length. So this is L naught. This length we will take as the original length. Okay. So just briefly, I wanted to help you guys understand the concept of tensile and the compressive forces and then shear, all right? The shear force. So this is it. So when you um, use the tensile or the compressive stress or strain, then you get the Young's modulus. Okay. But when you use the shear stress and the shear strain, then the proportionality constant becomes the shear modulus. So these two proportionality constants are being used to understand the strength of a material. One is Young's modulus or elastic modulus, another is the shear modulus. Okay. So is there any doubt so far? I hope I'm going at a slower pace, and I hope like you're able to catch up with whatever I'm saying. So is there any doubt? Then let me know. So let me quickly finish up this slide. Then we will wrap up. All right. So you can actually measure this modulus, tensile or compressive modulus, using a machine called mechanical testing machine. So this machine looks something like this. This is a mechanical testing machine where this is the head to which a load cell is attached. Here, load cell should be written. So here, load cell is attached. It basically controls how much force is going to be added. You can control the amount of force that you want to supply externally to the sample from here. And to this load cell, some jaw is connected. These jaws are used to hold the sample, and depending on the amount of load that you have you have given as input, these jaws will pull your sample. This is the tensile. That means you are giving tensile uh, forces on your sample, because of which some tensile strain will be generated, and proportionally some tensile strain will be generated into your specimen. So this is your universal testing machine, and this is how it looks like. Okay. Now you can either do uniaxial, means the forces are like experienced with the specimen along only one axis. So for that you have to use a dumbbell kind of specimen, like a dog bone shaped specimen is used. Okay, and we measure various parameters. Okay, while testing, we first, as I told, we measure the elastic modulus. Right. So this machine actually help you plot the curve like this. With stress versus strain, you will get a curve like this, where there will be an elastic region, there will be plastic region. Okay, so this kind of curve you will get, and from this curve, you have to calculate some parameters. So from the slope of the elastic region, you will get the elastic modulus, right? Then you will also be able to calculate what is the yield strength. So yield strength refers to the amount of stress, okay, amount of stress, uh, like from where the material has started becoming plastic. So it is the stress at which a given amount of plastic deformation occurs. Means, so this is your elastic region, and then so this is for 0.2% yield stress. Yield stress they are measuring, means the stress at which 0.2% of plastic deformation has taken place. That is, it is given by that this graph. But you can also calculate here as well, where this point where the elastic region is ending and the plastic region or plastic deformation region is starting. So at that point also you can calculate the stress, and that stress will be called yield stress. And here this point will be 0.2% yield stress, means the stress at which 0.2% plastic deformation has taken place. Then we can also estimate what is the ultimate tensile strength. Basically, it correlates to what is the amount of stress, maximum amount of stress that the material has experienced before it fails, means it breaks off. Okay, before it fails. That is the ultimate tensile stress. So here at this point, you can see the curve is ending. That means the material has failed. And before reaching that point, it has reached a peak value of stress that it has experienced. That is the ultimate tensile stress. Okay. And the area under this curve is the measure of your toughness, means how tough your material is. So you can see this curve alone gives you so many parameters. And these parameters are often reported to tell you the mechanical properties of your specimen. Okay. So then let's wrap up today's class now. If any one of you have any queries regarding anything that we have discussed so far, then let me know. Any queries so far?
No, ma'am.
All right. So tomorrow I was hoping to keep our class during the afternoon, like from 1 to 3 p.m. So is it fine? Is it fine for you guys to join at that time? Yeah? Yes, no?
Yes, ma'am.
All right. So we will have our class tomorrow from 1 to 3 p.m. in the afternoon time. I'll also post in the WhatsApp group so that others who haven't joined will be notified. So let me stop sharing. stop the recording process.